Let's move on from string theory to philosophy of string theory with Richard Dawid, a local hero from Stockholm University, often described as physicist slash string theorist turned philosopher, right?
And I never really was a string theorist, but
a physicist. But that's often the label you get, right? It's anyway. But take it away, please. Thank you.
Thank you. Thank you very much for the invitation. It's great to be here and really interesting. I want to talk about some work in progress with Guy, and more specifically about one part of it, and the part of it that is related to string theory. So I won't talk too much or use the term emergence that much in the talk. However, what we're discussing is quite closely related to the issue of emergence. And in the end, if there is time, I will say a few words about the connection, I think, that's interesting between this proposal and an understanding of emergence. So let me start in a very general philosophy of science way by introducing one core question or matter of debate in the philosophy of science, which is the scientific realism debate. And scientific realism canonically, and I say canonically because as always there are some variations of positions that frame things a little differently, but canonically the understanding would be that I'm a scientific realist if I assert that well-established theories tend to be approximately true, and that scientific objects posited by well-established theories tend to refer to something in the external world. So scientific realism, understood that way, is linked to an endorsement of the ontology that is posited by the given scientific theory. That seems to be quite at the core of what scientific realism amounts to. Now, let's move to the physics side of the story, and in particular to string theory, which, of course, after the last excellent talk, doesn't need an introduction per se. But I want to highlight one important aspect of string theory that will be crucial for our discussion, which is string dualities. String dualities are an important, very central feature of string theory. The understanding is that dual theories are empirically equivalent to each other, but they can differ in quite fundamental characteristics. What is important to point out that dualities are properties of formulations of the full theory, even though the entry point to those theories often is perturbative string theory. So when one starts understanding what a certain type of string theory, let's say, is about by pointing at the perturbative theory, but the understanding is that once I talk about the dualities, I talk the dualities in the context of the full string theory. So that means that dualities actually are means of reaching beyond the perturbative regime, and this is why they are so productive and so important in the context of string theory. Duality relations will be assumed to be exact in this talk with is the canonical understanding, though not everyone does fully agree with that understanding. Now, in string theory, we have a fairly extensive web of dualities, and I list three important cases. There is a T-duality that links one type of superstring theory to a different type that has an inverted compact radius of an extra dimension and exchanges transversal momenta and winding modes on that dimension. And that is important, and that plays out in string theory because we have those additional compact dimensions for extended dimensions that are observable. And the 6 compactified dimension. So you can wrap the string around that dimension, or you can, if you have a closed, you can wrap a closed string around that dimension, or you can give it a momentum in this transversal direction of the momentum. Both have spectra. Since it is a quantum theory, and it turns out that you find this T-duality that exchanges these set parameters and leads to an empirically equivalent model. What is important is that we are talking about superstring theories here, and in T-duality in superstring theory means that the T-duality leads from one type of superstring theory to the other. So that's down here signified by the T. So it connects different types of string theory. It's not a self-duality. Another duality is S-duality that links one type of superstring theory to a different type with an inverted value of the string coupling. So it links a theory, a weakly coupled theory, for example, to a strongly coupled theory and vice versa. So this web of dualities connects the 5 types of string theory that can be built via the intermediate step, or let's say, of M theory here, about which we have heard a lot. So there is in this case there is a kind of S-duality relation that expresses, in the framework of M theory, expresses the coupling constant in terms of an 11th dimension. Then there is another very important duality, important for full understanding of what happens in string theory, that is gauge-gravity duality. More specifically, what is understood at this point, ADS-CFT duality. And that's a duality between a string theory on the dimensional ADS space, anti-de Sitter space, and a D-1 dimensional conformal field theory on the boundary of that space. Once again, that is a well-established conjecture in this case. It might be a special case of general gauge gravity duality. The problem is the Sitter space, which would, of course, empirically fit best with what we observe in the universe. And first, no gauge gravity formulation that involves the Sitter space has been found. Second, it's not clear whether there are stringy solutions in the Sitter space. So it's not clear how general gauge gravity duality can be formulated, but the prospect, the hope would be that there is something of that kind in the end. Now, if we look at the effect this web of dualities has on the issue of scientific realism, the question arises whether scientific realism can be upheld at all in light of string dualities. As we have seen, ontological scientific realism is normally understood or taken to assert the reality of one specific ontology, the ontology that can be attributed to the external world beyond the theory we're working with. This is about ontological realism, that is, let's say, the form of realism that focuses on ontological objects. There is a variation of scientific realism that de-emphasizes the importance of ontological objects and emphasizes the role or the importance of structure for realist commitment. However, as long as one aims to formulate structural realism, this brand of realism, as a form of fundamental realism, which meaning realism that points at something one might call the fundamental building blocks of the world, then one would read structural realism also as specifying identifiable structural characteristics that are approximately true. And you have quite comparable problems. Also, if you characterize those various types of string theory or quantum field theory that are connected by dualities, you characterize them in terms of their structure. These structural characteristics will also be quite fundamentally different. So none of this seems to work in the context of string dualities, as long as one, let's say, one keeps this naive understanding, or the straightforward understanding of what is meant by scientific realist commitment. Because if we look at what changes when moving from one theory to the dual, most of the things, or basically everything you can think of at a naive ontological level would change. You'd get different dimensions of fundamental objects, and in brackets I always suggest the kinds of dualities that would have that feature. You change the gauge symmetry, you change the dimension of background space, the geometry of background space. You change a theory that has gravity in it, replace this by a theory that has no gravity. So it seems that if I want to have an ontology of the world, and I move to a dual picture, that dual understanding will undermine that ontology. So the question is there any way, any place for scientific realism at all in the context of string theory? Now, there is one position, a vague position, let's say, so it's not a one coherent view to which a group of philosophers of science fully subscribes, but it is something that kind of emerges as a suggestion as to how one can move forward with respect to realist commitment, and that one could call common core realism. And it has been pointed at or hinted at by authors such as Matsubara, Richtus, Hagen and Friedrich, Dihauer and Butterfield. And the idea would be the following: a search for what is real about theories with dualities should focus on the common core that is shared by all those theories. So one should just try to find a method of identifying that common core, and that may not be very intuitive then, what one has. But still, if one wants to be a realist, one should start there. So that would provide a natural basis, or maybe just a natural starting point for realist commitment. That would be the idea. And of course, that's a plausible and natural idea, one may say, thinking about the difference between what is reified and not reified in scientific theories as we know it. So, for example, if we have a choice of coordinates to characterize a theory, we understand that due to the fact that we have the possible to vary that choice of coordinates, that we don't reify that. We won't be realist about a coordinate system, but we will ask the question: okay, what is invariant under these transformations? So what is the common core of this? And then I have something that looks like a candidate for scientific realist commitment. Now, there is another aspect to this, and Dihauer and Butterfield in particular also consider that aspect of the story. One might say that not all empirically equivalent representations that are connected by duality relations are play out at the same level. So they may be empirically equivalent, but nevertheless, there may be some conceptually based hierarchy between them. For example, one may say that there are some reasons to think that M theory is more fundamental than the 10-dimensional string theories, or there is some reason to say that in ADS CFT, CFT is the more fundamental perspective. I don't want to go into that, whether or not or to what extent that is plausible, but if you find some hierarchy of that kind, of course, another option sorry, would be to say that I'm justified in having ontological commitment or realist commitment with respect to the ontology of that theory that I'm pointing at, that is kind of hierarchically higher up in some way. So those would be some options out of that problem, and those suggestions would provide a basis for saying, well, at the first sight, it seems that it's very difficult to be a realist, but thinking more closely about it, there are options. You can have realist commitment in one way or the other. Now, in order to think a little bit more about this common core idea, I will spell out the most developed form of a theory of the common core that has been provided by the Hauer-Butterfield. I will be very short about this, just in order to then be able to argue briefly what the problem in the context of string theory is if one tries to use that as a basis for realist commitment. So what the Hauer-Butterfield argue is that actually you can have a very general and generic strategy of identifying a common core of a theory. So if you have a duality relations, you can follow this and end up with a common core. And the idea would be that you describe the theory in their terminology as the common core theory, and that theory consists of numerically measurable quantities Q, states of the system, and the dynamics that specifies the allowed sequences of states. Now, the duals are in their terminology models of that theory that share that core theory, the quantity, states, and dynamics, that triple, but they have some extra structure that goes beyond that and that distinguishes among them. And in that extra structure, on that understanding, we would find these, let's say, intuitive ontological ascriptions that we would normally associate with ontological commitment, and that on that understanding then does not easily work, let's say, as a realist commitment. What one should be realist about is this core theory spelled out in terms of that triple. So that can deserve realist commitment. And you might, as said before, then for some reason go beyond that, but that would be a starting point for realist commitment. While the extra structure would be more suspicious, let's say, if we don't have any very good reasons to emphasize that. Yes. You mean the core theory? So if all that you attribute to the specific formulation of the theory, so the ADS structure, the string theoretical understanding, all that would be extra structure, and on the other hand, the gauge, the conformal gauge theories formulation, that would also be extra structure. The spectra, and then that links the two, that would be the common core. And that's the general idea about this. Now, and we will come to an issue related to this very narrow understanding of what you can spell out as a common core. So what we now suggest is a very different take on the issue that starts with what we would expect from realist commitment, what we expect realism to provide us with. And that view, I will spell out that view in terms of string theory and how it plays out in the context of string dualities. But it turns out that it is also very helpful for understanding of the issue of realism in the context of quantum mechanics, and specifically in the context of the selection of tensor product structure, where comparable problems arise, and where what we propose, we argue, can also be helpful for having a better grasp on what's going on there. And in the paper, the connection between the two plays an important role, and we think mutually strengthens the cases for each of those representations. However, due to lack of time, and also due to the fact that this is a meeting about space-time emergence, I will focus on string dualities. And if you're interested, we can talk about this connection in the discussion. And since Guy is a co-author, he might also have something to say in the discussion about this. So, okay. So let's move on to the issue of the role of realism. So why are we interested in realist commitment at all? And one way of framing this, one popular way of framing this, is in terms of the motivation to explain why a scientific prediction is successful. So there is a core argument of in the scientific realism debate in favor of scientific realism that is called the no miracles argument, and then that claims that scientific realism is the only way to explain the predictive success, the novel predictive success of science that otherwise would be a miracle. So in order to play that role, however, realism must be based on a concept of theory that can be the basis for extracting empirical predictions, because these empirical predictions are what we want to explain by realist commitment. And the question is, what does that mean for this debate, for the debate of realism in the context of string theory? In order to sharpen this role of scientific theories a little bit, we use the theory concept proposed by Daniel Dennett that frames scientific theories as compression mechanisms that allow to represent data sets in terms of substantially fewer bits of information. So the idea is that prediction is there, novel prediction can be there if a theory has that characteristic of being a compression mechanism. So linking this view to scientific realism, a no miracles argument would be based on the observation that a given theory is a successful compression mechanism. Therefore, we need a definition of a theory that gives us that does represent theory as a compression mechanism. And the question then becomes, does this work if we define the core theory along the lines of the common core in the context of string theory? And the problem now is that in string theory, first, one does not know the full formulation of the theory, so there is no known model-independent formulation of equations of motion of the theory. The starting point for a formulation of a calculable theory is a perturbative expansion in terms of interacting strings. So one starts with types of string theory, and one starts with actually the perturbative expansion of those types of string theory, and then one can do something with the theories. The duality relations then connect the various types of string theory based on these conjectures, let's say well-founded conjectures that are based on comparing the spectra of those various theories, and establish them as empirically equivalent. So these duality relations are the most important, let's say, means of reaching out beyond the perturbative regime of those models, while the dual models are the basic, or remain the basis, for quantitative calculations of the theory. In other words, if we want to understand the entire, let's say, complex that is string theory in terms of a compression mechanism, we need to include the models in our representation of what the theory amounts to. If we just point at the common core, we won't have that. Therefore, what is known about string theory at this point provides no basis, we argue, for viewing the triple of states, quantities, and dynamics as a compression mechanism without relying on models of the theory. So what is important, of course, to point out that this is a characterization of the current state of understanding of the theory. This may change. Lots of things may happen in the future when it comes to the understanding of full understanding of the theory. However, one would not want either to insist in an understanding of realist commitment with respect to the theory on a specific hypothetical and maybe not very likely trajectory of further development of the theory. So the idea is, if we want to think about realist commitment about the theory at this point, can we do that already based on the way the access to the theory we have at this point? And then the conclusion would be that the compression requirement cannot be said to be satisfied by the common core in this context. Now, there is another issue related to this context of string dualities that suggests attributes a more important role to the models when expressing realist commitment to the theory. And that point is that the fact that there is this web of duality is itself a matter of having a more extensive understanding of the theory than just pointing at the common core. So once one has found a model, it is possible to infer the duality relations to other models. And even then, even at this point, of course, it's never clear whether all the duality relations have been found. I mean, the history of finding duality relation is a history of discovery. And normally, what one would have is a situation where one there's different formulations, and then after the fact finds duality relations between them. There may be exceptions. M theory may be a specific case where the inference to M theory is deeply associated with the understanding that there should be such a duality relation. So this is all not always that easily separable, but often one would say that the specifying the models is the first step. So it is a matter of representing the full theory is a matter of representing the duals and understanding that they are dual to each other. So the duality structure itself seems to be a crucial characteristic of a theory. And if one wants to represent a commitment to the theory, one would want to represent that commitment as the commitment to the existence of that duality structure. Now, that is, at that point, still a very general observation. However, one can make that a little bit more precise if one tries to point at the role those duality relations play. And that role is to identify ground state to identify neoclassical limits of the theory, and we will come to that. But first, I want to start now on this basis with defining realism, and then asking the question: okay, so how does this connect to ontology? So the idea now is, we have seen that the common core does not work as a basis for realist commitment. We want to have an extensive understanding of realist commitment in that case, that includes those various representations, and that does not insist on singling out one or the other representation. So that would be more akin or to the process of argument that, for example, we have also seen in the last talk, right, where we speak about one context and then one applies the duality relation to understand the theory better, and then moves on to maybe another duality, moves on to another representation. So one tries to have a full understanding of the theory by exploiting these duality relations. And at some stages, it's not that awfully difficult for acquiring this full understanding to insist to be in one of those dual representations and stay there. So it's not about one of the models, it's not about the common core, it's about the overall picture one tries to project. So that would mean that realist commitment is about that full theory, whatever that means. Of course, that then raises the question, so what does realist commitment then mean? And if I have time, I may give some thoughts on that at the very end. But at this point, I just want to leave it at that. So saying that's what we want to be realist about when we are realist about the string theory. But that means that we have no place, it seems, for ontology when spelling out realist commitment anymore. So what is ontology then? So the proposal is that ontology is not wedded to realist commitment. There is no real ontology of the fundamental theory. Ontology, on this understanding, however, plays an important different role. So it's not that the case that this that drops the significance or reduces the significance of ontology, but the idea is that ontology points at something entirely different at a fundamental level than realist commitment. Ontology gives us an intuitive understanding of the way the fundamental theory connects to what we observe. So it is something that is connected to the observer's perspective, while the realist commitment with regard to the fundamental theory is not. And in the following, I will try to explain why we think that's a plausible position in this context. So what dualities do, or can do, let's say, is they can lead from something that looks neoclassical to something that is deep quantum. So in the most straightforward way, this plays out in the context of S-duality, where we have the situation that it connects a theory, a weakly coupled theory, neoclassical, to a strongly coupled deep quantum theory. In the case of T-duality, it connects one theory or model that has a very small compact dimension to another one, another type of theory that has a very large compact dimension. So in the very large, if you have the very large compact dimension, then you have a nearly continuous spectrum of momenta, possibility of localization, and so on. So this looks like a classical situation, while if you have the very small radius, that's not at all the case. In the case of ADS, you connect a theory where in the ADS, on the ADS side, where curvature is small, to a strongly coupled field theory and vice versa. So once again, you have a neoclassical scenario on one side and the deep quantum scenario of the other side. So there is a sense in which dualities establish that there are several very difficult, different classical limits of string theory. So the web of duality is a representation of that fact. Now, this is established with regard to models that are the basis of entirely, though they have entirely classical limits, are the basis of fully empirically equivalent formulations of the theory. So what one has here is a situation where I start with one type of theory in a neoclassical limit, then the duality links that to a theory in deep quantum, and then we find the parameter that we can change in order to once again find the neoclassical limit of that other theory. So then we have found a solution of the theory that represents a different neoclassical limit. So by moving from one model to its duals, one identifies those various classical limits. Yes. Yeah. No, they don't. They don't, because they are the same predictions are on that line, right? No, they are not. We know that they are not, right? The duality connects specific parameter models that represent specific parameter models, values of a theory. And if you think about this in terms of a string landscape, that would correspond to one specific local ground state of the theory. And that would be this link, right? So it links the theory here, let's say, whatever, type 2A, type 2B, down here, and up here, right? So you have you have a connection between empirically equivalent specifications of the theory, or let's say ground states of the theory represented in terms of different types of the theory, but they are not all in the neoclassical limit. What you need to do is, in order to get to the neoclassical limit in this context, is you need to change the parameters, which means you need to move to a different ground state of the landscape. So that is empirically different, and that's the crucial point, actually. So these things are not empirically equivalent. They are different classical limits of the theory that represent different phenomenology. And in terms of string theory, you would say they represent different phenomenology because they are represented by different ground states of the theory. So that's the idea. The duality is this, but the set of classical limits is down here. And this connection is needed in order to tell the full story, let's say. Yes. Well, for example, you have a theory, a certain type of theory with a strong string coupling, and with a small string coupling. This is the same. Well, it's so you have formally differently structured theories, and that characterizes, let's say, the naive ontology, right? So if you talk about a certain type of string theory, you would have specific gauge structure, you would have specific branes of specific dimensions, for example. You would have and so on, right? So all these things can change with respect to the types of string theory, but they would not change if you just play with the coupling constant. So the idea is, okay, let's say the naive idea would be, all right, I have those different types of theories, they correspond to different ontologies, and then I have, as we always have, I can play with the parameter values, but the parameter values don't change the ontology. That's the idea. So in this sense, it is the same theory. It is a theory that has the same ontology, let's say. But of course, you would say it's a different model. And in terms of the overall understanding of string theory, you would say what it means to say it's a different model, it is a different ground state of the theory, nevertheless. So each ground state of the theory, however, can be represented this way, or that way, or any other in the web of dualities, in any other way. So you have those different representations of the same ground state, and you have different ground states in the same representation. So those are the two, so to say, orthogonal directions in which you move. One is that direction, and the other is that direction. Yes. So what you can, I tell you what you can say and what you cannot say, right? What you can say is every ground state of the theory can be represented here somehow. Can be represented here. What you can also say is that given that is a duality, a universal duality in string theory, from here you can always have a duality translation to somewhere here. And if that's a solution of the theory, that's also a solution. So if what you cannot say is if I have established in some way, and normally you can't, you cannot extract the exact values of low energy effective theories based on string theory. But let's say we have established that this actually is a ground state of the theory. Then I move here. And then I ask the question, is there also a ground state of the theory that is in a low coupling limit of this? That's logically not implied, right? In principle, you might say, no, unfortunately, there is none. This theory does not have a solution in the neoclassical limit. However, the expectation is there is such a huge number of ground states that you will always be able to construct a solution in that vicinity. So you will always find neoclassical solutions of each of the types of string theory. That would be the expectation. But this expectation does not follow from that scheme. It's just a matter of the understanding of the size of the landscape. Is that? Yes. Mm-hmm.
Classical theory, like classical PR plus classical
theory. Yeah. Right. So if let's say the ADS solution that you describe is here, right? So what you would get then, so this means that you have let's say a small curvature solution of in ADS. So you represent that on the boundary, and you get a conformal theory representation of that, which would be a strongly coupled theory. So the story then would be, however, now we are on the boundary. So we ask, what are the solutions of the theory, and what representations of systems can be expressed in terms of that boundary theory? And then we look at weakly coupled solutions. Then we go down here. That's the logic. Yeah. Okay. Thanks. Yes. Exactly. Yes. Yes. That's more or less our conclusion. That will be our conclusion. If we knew in which corner we were, or if string theorists knew, let's say, then one could answer the question. But there is no way of telling at this point. All right. So we have this situation that the fundamental theory has these several classical limits, and each of them is pointed at by the neoclassical limit of one of the types of string theory. So then the idea would be that the ontology of a given type of string theory links our intuitive observational perspective, perspective on the full theory, by pointing at the way in which that theory assumes features in this neoclassical limit that can be related to our intuitions. So the idea is, I think something went wrong with that sentence actually, but the idea is that we have an ontology that in principle can be attributed to the full theory, because any type of string theory can represent the theory. That ontology, however, may correspond to the neoclassical limit, for example, as you said, we happen to live in. So if that's the case, then we can say this ontology tells us the ontological outcome of the theory in that classical limit. And now we may have other classical limits, so we may not want to talk about our world, but about other possible worlds or other actual worlds, if we think about it in terms of a multiverse scenario, for example. And then we say, so there are other ontologies that explain the theory in terms of that observer's perspective that sits in this other solution of the theory. Which means that the ontology is about singling out the type of theory that has the classical limit from which I'm looking at the universe. So the classical limit in which my experiment is placed, let's say, that I use to test what's going on in the world. In the deep quantum regime, none of those concepts keep their fundamental significance, right? It's then not awfully helpful to talk about space or to talk about individual strings, or let's say individual two branes in the case of M theory, if I actually cannot isolate those. So they are a way of formally representing it. But the question is whether it's awfully meaningful without our other reasoning to call that the ontology of the world, given that it's just a kind of a representation of a system that is strongly coupled, where I'm never in a position to isolate the individual objects that I'm pointing at. So that then draws the distinction between realism and ontology, because ontology is about those classical limits. It's about our perspective, while realist commitment is not. Realist commitment is about the approximate truth of the theory. And the theory, of course, should give all those neoclassical limits and explain all the options an agent has to sit somewhere close to that classical limit and make any observations. So all the ontologies kind of emerge from the full understanding of the theory, or from the dynamics of the full theory, if you want. And commitment to that full theory plays out at the level of realist commitment, while commitment to a certain perspective plays out at the level of ontology. Okay, so I think I can skip that. That's just repeating what I said. I might say a few words about effective theories, because that may make it a little clearer what is going on here. So we have those two directions in which I can characterize my perspective on the theory. One direction we have talked a lot about already. This is the distinction between a neoclassical limit and moving away from that to the deep quantum. Sorry. The other direction would be to move towards low energies. So if I move towards low energies from string theory, at some stage, I will lose the concept of extendedness, because the energy scale at which I characterize the situation is an energy scale where that extendedness cannot be dissolved. So I am in an effective field theory with point-like objects, and that effective field theory, of course, will be a low energy limit of that high energy theory. So I will have, going down from string theory, I will have I will break supersymmetry. I will end up with four-dimensional theories if the other six are compactified on small circles. I will lose heavy particles, and at some stage I will end up with a standard model. And that is connected step by step, moving up again to the near classical limit of string theory, where the theory is represented in an effective picture by weak coupling constants, so that I can have a normalization group running down to my energy scale. So what I have here is a scenario where at some stage in this story, fairly early on probably, I will lose the duality relations. So the low energy theories won't have the duality relations anymore. Therefore, the low energy theories lose the spectrum of the spectrum of near classical limits. So for the low energy theory, there is only one near classical limit left, and that's the one we are in, so to say, and that links up to the given near classical limit of string theory, from which this tower of effective theories leads us down energy-wise to the world we observe at the LHC, let's say. That means that from the effective theory perspective, the connection between ontology and realism is very plausible, because the realist commitment to my effective theory, the effective realist commitment, if you want, is associated with commitment to one ontology, the ontology that happens to be the ontology of that neoclassical limit. Therefore, from looking at the situation at lower energies, the realist intuition that there is some connection between ontology and realist commitment is very plausible, very natural. Only once one ends up at high energy scales, where the duality relations open up, and where it turns out that there are those solutions of the theory corresponding to various neoclassical limits, this connection breaks. So the idea is, for all low energy purposes, this is fine, attributing connecting ontology and realist commitment, while at the Planck scale, at the string scale, it's not helpful anymore. One should carefully distinguish between those two concepts. Okay, so I'm nearly done. The idea is, this is just repeating what's been said already, that there is ontology that is observer-based, and there is realist commitment that is observer-independent. And the idea is that at low energies, you don't see that distinction, but once you move up to the high energy scale, you do. And then, therefore, those two things fall apart. Thank you.
Okay. And then also